putting together these slides, we're really reflecting on an incredibly exciting year in deep learning, and general deep learning, where you're seeing these kind of really incredible technologies start to hit the mainstream in a big way. And so what I wanted to do in this talk is really maybe uh, try and say a little bit how I see the wider deep learning landscape and how these techniques might impact or might not what we're doing in structural biology. And so, how ML has changed in the field, and I really mean especially in the last year, but over the last couple of years. There's been a very big shift in even what people work on and what's seen as current. And so, like, the two big shifts have really been around, I would say, have been in the field of what's called generative modeling, how you get deep learning models to produce things like text, images, etc. And it's been driven in two ways. One is really this class of models called diffusion models, and the idea goes back maybe even to something like 2015, but has really been refined and popularized recently, and has become the generative model of choice for basically anything that's not text. And so a lot of the really exciting things, for example, you see in generative modeling of images, and very recently in generative modeling of proteins, has been diffusion related. And actually, kind of interestingly, I think I even see, mentions of GANs, for example, as completely dropping off in deep learning conferences, that this is almost entirely displaced GANs as the generative technology of choice. We're seeing some extremely large, and I'll talk about why they're so extremely large, text and image models, and really kind of this coalescing of a notion of a scaling hypothesis, a real data first view of deep learning. Also seeing some interesting technical trends within this, where if you squint at them, they're growing MSAs, and I'll talk about that in a minute, but language models that really have retrieval as a first class component. And I realized I didn't talk about this as much, but a lot of really interesting work in how you deploy these in terms of fine tuning and how you build kind of what are called prompts and other things. And at the same time as there's been all this kind of exciting work about how you set up the learning objectives, what you do, there's actually been it's been much, much quieter in terms of deep learning architecture, the kind of core components of neural networks that for the most part, transformers and to a lesser extent another architecture called UNets have pretty much won in most of the non-scientific deep learning applications. And so there's a real question here where now the favored research is really around data and scaling rather than thinking about architecture. And it's very interesting to think what that may mean for our field. So outline of the talk, and I'm really going to talk about these two kind of main things, generative models and diffusions, and especially the connection to multi-state sampling. Protein language models, or various ways in which language models can hit our protein tasks, and how this relates to the scaling hypothesis. And I'll talk a little bit about next problems. And what I also want to point out is how many of the problems that we have aren't immediately addressed by these, that I think a lot of it will still have to come with innovation within our community or very specific to proteins in order to answer a lot of the questions that biologists have, even though all these other technologies are going to make an impact on our field and already have. So when kind of thinking about this, I want to just situate this in multi-state modeling, and I just want to remind everyone that kind of Anfinsen was wrong, right? Or at least Anfinsen was approximately correct and was very useful, but he's not quite right. That you can't really talk about the single structure of a sequence, of course. Proteins have multiple states. They're condition dependent in various ways. And a lot of times biologists really, really care about this, right? That you're really talking about things like differences between the active and inactive states, for example. What has changed? What does this mutation do? And so thinking about multi-state modeling, as CASP is starting to include, certainly is important. And the current state of the art actually is somewhat okay. At least it hasn't been assessed in CASP yet, except probably in this one. I'm sure it'll be talked about a bit, but the current state of the art is really, if you want diversity out of your outputs, it's to make the problem a bit harder for structured prediction networks like AlphaFold. So this is basically reducing the MSA size intentionally, throwing away parts of your MSA, subsampling, and originally done in an undirected manner in the Del Alamo work, and then in the more recent work by Wayman Steele, even doing it by clustering the MSA and throwing out chunks of phylogeny at a time. And this really does generate, for one thing, it generates more diverse answers. And the second thing is that it's often meaningful diversity, that it's often along, say, natural components of motion, of transporters and other things. So we are seeing some examples, and I wouldn't say we're at all satisfied with the level of diversity that we get out of these, but we are seeing kind of ways to get diversity out. And this is a lot like the situation with AlphaFold, the original AlphaFold monomer, and multiple and protein binding with the linker trick. It's not that it was exactly trained for this, but it's trained in kind of a physical manner. And so that's a related enough problem that if you play with your inputs carefully, you can make it do protein-protein interaction, as people have shown. This is the kind of dual of this, is if you play with your inputs type thing, you can get multiple states out of it. Now, I would say the most probable explanation in my view of how this works, I mean, there's some explanations of, oh, well, different parts of the phylogeny have different states. And I don't, that's possibly true for fold switching proteins, which some of the work considers. But if you're looking at something like, say, a kinase, you're not going to say that, you know, DFG in and DFG out are really properties of different kinases in the evolutionary tree. You'd say they all have those states, and what you're really doing is mucking around with the initial part of the structure prediction process where the network is highly uncertain. And I quite like, I took Sergey's, from Sergey and James Roney's paper, really looking and thinking of this as as having a rough energy surface that represents kind of the basins that say AlphaFold can fall into. And if you reduce the MSA, you kind of get some randomization early on. And so you win it kind of in the later parts of the network when it's really locking down and refining a hypothesis, maybe it ends up refining a different one. And so these kind of methods work a bit. And I think it hasn't been quantified exactly how much they work. We don't have really good benchmarks in general in the multi-state field, but they do definitely sometimes work in anecdotal cases, but they're not really principled. What's the kind of principled and good way to think about multi-state modeling? How should we connect this more directly to a deep learning objective? And so one answer to this, and what I think is likely to be the answer, has come out of, you know, this kind of jargony phrase, conditional generative modeling. So generative modeling means, you know, I want to give many answers. I want to give a distribution of answers. And conditional means I know something. It's not just generate me some image. It's give me an image, in this case, that matches a caption. And so people have gotten, and people have trained some really shockingly good networks for this. This comes out of the DALI network, but there are many related ones. And the input to this network is a totally underspecified thing, just like structured prediction is underspecified, but far more underspecified. The input here is a dolphin in an astronaut suit on Saturn art station, as a caption. And given that caption, I think you can agree that whatever image is there somewhat represents that concept, but it's by no means the only image that can represent that concept. And yet it's very, very convincing in details, that all the details are kind of consistent with this. And this is something that we want in proteins. We want especially things like allostery. We want distant parts of the protein to have very kind of meaningful relationships between them. We want that to be consistent. We want the neural network to kind of think about and encode those things. So what's the clever idea that got people to this, and why is it called diffusion? Well, let's start with a very, very simplified view of protein structure prediction or deep learning protein structure prediction. We have inputs, we put them in a network, and we get a structure out, right? Okay, and the network has parameters and we learn the parameters. Okay, or at least this is how we would use the network. And then how do we train the network? How do we get those parameters? Well, let's just add a red block of the experimental structure. And so we've produced a structure and then we have an experimental structure and we measure the error between those two. And since the network itself is a mathematical function, given a set of parameters, this is all kind of a deterministic thing that even though the problem is underspecified, what is the structure of the sequence, it will produce some structure from that sequence, and it will do it to try and minimize that error on average. You can also think about that as minimizing that error over all possible states. And so we try and write down a clever error function for this underspecified problem that will get us the kind of properties we want. And in AlphaFold, the answer we gave there was FAPE, which has some nice properties that I won't go into. But in general, this is kind of a very, very simplified view of non-generative of single answer structure prediction, Anfinsen structure prediction. But we really want to tweak this in some way. We want to keep most of what's good, but how can we think of this as a generative problem? How are we going to kind of map this? And the answer we'll come up with is we'll just add another input. Somehow we've got to get some randomness into this. And the standard answer for randomness is I'll give you a source of random noise. And the very clever idea of diffusion modeling is that the source of random noise will be a blurry version of the image, or a blurry version of the output, the right answer, and or with added noise. And where this kind of came from, I guess, what's the best way to think about this? Is this, depending on how much noise, this is a lot like templates in a sense. You could think of these as kind of like templates, right? Templates contain a related structure, but not exactly the same one. And so, for example, if you provide AlphaFold with a really strong template or another network with a really strong template, then you would expect the network to listen to it a lot, that it almost doesn't have to look at the inputs if the template is really, the other inputs, if the template's really strong, it's just kind of fixing up the details of that template. If that template is really far away, if it's a really poor template or really distant homology, you might learn a little bit. Sometimes you can learn a lot, but at some point you'll even start ignoring the template. You'll rely more on the other inputs like the MSA. Well, this is like this. It's not a template, but the input is basically the coordinates of the structure with added noise. And if you add a little bit of noise, then you're kind of looking at refinement. If you add a lot of noise and it's kind of uniform Gaussian noise, then you get less and less information until you add an absolutely enormous amount of noise. And then basically there's no information in that noisy structure that can be extracted. And so the diffusion process is to train a neural network to do this denoising task. This is the first part. So at training time, you sample a random amount of noise from a little bit to a lot. And there's all sorts of papers and details on this kind of thing. But you add different amounts of noise and you train the network to remove noise no matter how much you put in. And so you've made something that's kind of cool. You've made a protein denoiser. But why is this a good thing? How does this relate to what we ultimately wanted to do? I don't have a noisy version of the structure. If I had that, then I would be fine. Well, maybe in cryo-EM I do, but in general, I don't have a noisy version of the structure. How are we going to use this thing? And so the really neat trick they found out, and the trick that honestly looks a lot like, in my view, recycling, is, well, suppose you would train this thing. Well, we can start with so much noise that we're just a uniform Gaussian. We can start with an enormous amount of noise. And then we can run it through our denoising network for a step and produce what it thinks is the denoised answer. And then we can basically feed that back through. And what you really do is you take a little small step toward the answer and then feed that back through. And you can run that again and again. And so what you've built is really you built a denoiser that can work at different levels of noise. And then you just take absolute static, right, absolutely random noise, and you feed it iteratively through this denoiser. And when you do this, and you can totally ignore the equations on here, we're here for the picture of the dog. If you think about this when you're, for example, training and you start with the image of the dog on the left and you add more and more noise, you can see that there's different problems at different levels. But by the time you get all the way to the right, you can't see the dog. That's just generic noise. But then when you basically are running this network, which is really good at finding patterns even from nothing, then it will eventually kind of spread out, and by feeding it in random noise, you can get a wide diversity of answers. And I'll have to say that, like, it's a very clever idea. What I don't think anyone can really explain why this one is the very best idea that we found in generative modeling, but what is really clear is that it lets you train quite expensive networks, right? Because each network is trained to do only one step of this denoising, or the network is trained only on one, but you'll run it out tens, hundreds, thousands of times to go from pure noise to an image. So you get a very, very expensive network trained relatively cheaply, the same kind of trick that we use in recycling. Excuse me. But this has proven really, really powerful at modeling different processes within image. So basically all the kind of really impressive, like that dolphin in an astronaut suit, is all coming from this process, which is refining. And one of the really nice things about the refinement is it does more and more details as it goes. Now, quite a few people in the protein community have noticed and have made good use of the fact that diffusion is really great. And they've said, okay, well, what about, so, sorry, what about diffusion for proteins? And so, and actually, I'm sure I've missed a whole bunch of references. So there's been both diffusion in structure modeling, and this is Anand and I'll pronounce the second name wrong, outcome on this equivariant diffusion paper, which is where the image at the bottom comes from. But then also in the last few weeks, really impressive works on diffusion for protein design. Both methods where you're diffusing to getting the coordinates, and I think also probably in the Ingraham paper, diffusion to get the residue identities themselves. And this has gone all the way in the case of the RF diffusion, the Rosetta Fold diffusion paper has gone all the way to experimental verification. And in fact, almost certainly the state of the art in deep learning protein design is to use these kind of tricks. But I also see these tricks are certainly going to be used for multi-state modeling. I think they're almost certainly going to be good ideas. Have really, really displaced all the other generative technologies in anything but text. Text will use a different generative technology for reasons I think people still also don't fully understand. But we're in a really great place where we've got good ideas on how to build generative models. And then the question will be, is this what we need to do multi-state modeling of proteins, which is very different than images, but initial results say it's a good thing. So that's kind of been the diffusion story. And I think it's one that we really should be keeping an eye on. And we should also be thinking about how our modeling relates to it. Like, we have now powerful ideas for how to do multi-state modeling, but I don't think anyone really knows, for example, how to evaluate it, how to really figure out what the state should be, et cetera. So it'll be an interesting time with a lot of anecdotes in the next few years. And then, oh, yes. Oh, sorry. And then I guess kind of the second kind of part of the story that I wanted to talk about is language modeling. And this has been an absolutely enormous story over the past year and reached all the way out to, New York Times and all the media that you can imagine. And it's been, and over the there's been kind of two big stories. The one that's reached the New York Times is this autoregressive language modeling that I'll talk about second, but also mass language modeling in BERT for understanding text. And the difference between understanding is you could think of it as like answering a yes or no question or answering some question from the text. And then autoregressive is about generating text. And just like kind of diffusion, you're turning this problem you want to do, which is kind of grand, into a simple game-like task and then training it on a lot of data. And so if we start with mass language modeling, or BERT, which I'll sometimes call it after the first kind of approach to do this, it's a very, very simple task. It's fill in the blank. It's a little bit of, Mad Libs as a challenge. And so some examples of how this is done in language is the car was blank on the road and hit a speed bump. One possible completion there might be speeding, might probably isn't stopping, for example. You can start to see, like, as you start to fill this in, you have to know something about cars and what they do. If you think of another place in which this kind of fill in the blank task, they took a picture of the Eiffel Tower when vacationing in, the answer is almost certainly Paris. New York City is a very bad answer here. So just this simple task of, what's the missing word, requires you to know all the landmarks in all the capitals or in all the major cities, requires you to know quite a lot about the world just to fill in the blanks, because filling in the blanks is contextual. It's about the world. And there's another, for example, and even more on world understanding. Since Alice wasn't hungry, she took the could be sandwich with her, right? She didn't eat it then. But you can think of other things. So solving this really well, solving this a little bit, maybe just knows, is like the simplest way is just, well, these are the common words in the English language. Solving it a little bit better, you would think about, has to understand various co-relationships of words. And solving it really well becomes extremely difficult, becomes like understanding the world difficult to do it really, really well. And so people have tried to train networks really, really well to see what they learn and see how much world knowledge they can push in just from large amounts of text. And this has worked quite well. I mean, even in things like internet search and lots of other things, this kind of concept has really built networks that understand text at some level and can really extract some meaning out of it. And of course, this has been going on a few years and has actually a pretty strong relationship to covariation. So the task that you think about, like pseudo likelihood or Potts models or other things, is predict one part of a protein sequence within an MSA from the rest of it. And this task is much, much like the BERT task in a restricted way. And you can really think of pseudo likelihood as kind of linear BERT or linear mass language modeling. And you do the same kind of inferences, right? So I put two red tokens into the MSA on the right. And so you can kind of guess, for example, in the one in the bottom left, and I don't know if you can see my cursor, but it's not that important if you can't. But you can see that far left token is probably an S. You can guess based on homology, but you are looking at homology, you're comparing to related sequences. You can look at the token to the right and you can say, well, that's probably an L, it's probably a leucine based on the other sequences. I'll give you a hint. I looked in there and it's not, right? It's actually, I think, methionine. But you could imagine that this could become a really hard task. Like if you want to do this really well, you might try and answer questions like, is that site buried or did it just happen to be a leucine? What about in the other homologs? You could look down that column and notice there are some charged amino acids. So it's probably not actually a buried site. There's quite a lot of other, in theory, deductions that a neural network might, let's say, want to be overly anthropomorphic or might try to make to pick up on these kinds of correlations. And so this has been, you could think of this very generalized covariation, and this was done independently in the MSA transformer work, and that's classic kind of pre-training, just training on lots and lots of text, and then it's a part of the AlphaFold training, and you can see in the bottom left. So we train that, and we find that doing this kind of task makes the network better at shallow nefs, not extremely shallow, but shallow nefs, somewhat dramatically, somewhat surprisingly dramatically. And you can think of this as kind of aligning it and showing it covariation as a task, not by saying this is the formula to do it, but saying, oh, by the way, you should figure out how to complete MSAs too. Now, doing this, and this is not exactly the historical version or historical timeline, but you can just say, okay, well, that makes sense, right? We understand covariation. That's a good thing. But why did we need the MSA? The MSA is showing you sequences that are in the training set of a language model. Say if you were doing a single sequence, you could do the same completion task for single protein sequences. You could just have that information in the weights of the network. And we can ignore all this, MSA stuff and dealing with alignments, and that's painful and expensive and everything else. We'll just put it into more training on a bigger model. And we should expect MSA-free models to be much bigger, because just like, say, natural language models that are trained on this BERT task have to memorize place names, capitals, all the kind of world information that can help it complete. The analogy in protein language models is they need to memorize protein families, evolution. We don't have the full set of possible proteins. It reflects a kind of branching tree, and the network is going to want to remember that. But if it does this task really well, then it's going to want to learn structure and contacts and other things eventually, because that's very useful in this task of figuring out what could be missing in a sequence, right? Does it need to hydrogen bond something, et cetera? So ultimately, it pulls in all that structural knowledge just because it must, in theory. And these models, if you think about it, are trying to answer the question of what are the completions of this sequence such that the sequence could appear in uniprot or magnify, et cetera. And so there's been a bunch of work on this, especially recently, ESM2s, all the others. And it's really natural, I should say, I'm not going to talk about it much, but it's really, really natural to talk about variant effects, because it's almost exactly a variant effect network that we're then trying to go find structure in. But do they learn structure? And the first place to kind of look, and these are transformers, these are models with attention, meaning that they have this n by n map of who's talking to whom. And if you look at that and you extract it in kind of a careful way, then the answer is definitely yes in many cases, that it is finding out lots of what's called unsupervised or almost unsupervised contact prediction, where you can basically just look in this, and the task of trying to do this kind of silly complete the uniprot sequence task, well, it's learned a tremendous amount about structure and has a lot of understanding of contacts. And we shouldn't be too surprised, because there's a really, really close analogy between mass language modeling and coupling analysis. And we know that coupling analysis tells us something about structure. So higher order coupling analysis hopefully tells us even more about structure. But I think it also leads to an interesting question. I think there's been, at least I may be coming down on what is still a debate. Is this evolutionary structure prediction or not? We talk about these often as single sequence networks, which I think is not a meaningful term. At least when we think about systems, we all build single sequence systems, right? You put a single sequence into AlphaFold. If you wanted to call it a neural network, then our first layer is called jackhammer. And that we should take seriously. Okay, well, what's the difference? What's the kind of different behavior we're getting out of these? And all the information that a neural network might want to use to do prediction, including like knowledge of the common families, and right, the families repeat a lot, that will be in the network. So these neural networks, even if they take a single sequence, are definitely going to memorize things about large protein families, almost surely. And one way I've been trying to think about it, and others have been trying to think about it, is Well, if these were really, really like physical, you wouldn't care about the MSA depth of the family. And, the ESM2 paper does some careful work on this and shows quite clearly that, say, their behavior, their accuracy at unsupervised contact prediction is is very dependent on the number of sequences that they would find if they had built an MSA with MMSeq2. Not that they do use an MSA, but if you check MSA depth, then you can see on the left, and the different curves are different sizes of the SM network. So you can see it does get better for larger networks, but you see a very still strong dependence on this number of MMSeq hits up to quite large things, that this doesn't really seem to start saturating until something like 10 to the fifth hits. And the interesting part, and I won't at all say this is a totally fair comparison, so just treat this as, suggestive, but by no means conclusive. In AlphaFold, you see kind of behavior saturating at 30 to 100 hits, or more specifically, median per residue NEF. And okay, so there's a NEF to sequences comparison, but I think these are quite dramatic differences. And I think all the evidence is probably that these single sequence LMs are more MSA depth dependent than are MSA based networks. And, there's still lots of good things about them, and it's still a very active research area, but I think this is where we are at the moment, right? And they have speed and ease of use, and there's a lot of good things about them, but they seem to be more MSA dependent. Now, I know there's some like work on orphans and other questions, but I think it's all still very inconclusive, and it all still doesn't work all that well, although I guess we'll hear from the assessors later on some of these very difficult ones. And also say that in sequences that have conservation, but not something that's a tool like Jackhammer or MMSeq can pick up, these networks may be dramatically better, and there may have been some of those in this CASP. But actually, the kind of challenge of small MSA depth sequences is quite analogous to what people have seen in language, that these models that store all the information in their weights do really well on common topics, but have difficulty with kind of rare things, right? That one, fact that's somewhere in there, just like you can't remember every fact from your life, so you write things down. Language models have a similar problem, and common things get basically stored into the weights of the parameters of the network, but rare topics are much more difficult. And, so they've just done so the kind of solution within the field, or at least what people are working on now, is often heavily what are called retrieval based. That, I'll just pull out some snippets of text, kind of like snippets that you might see as results of a Google search, and I'll also present those to the network. And, DeepMind has done work on this, but all the kind of major language modeling teams have done a lot of work on this, and it really does seem to improve, and you can make neural networks that cite their sources and everything else. But I think the most fun part about this is if you squint at it, it really looks like introducing MSAs without the alignment. So maybe, unaligned multiple sequences. But the kind of, I guess, trend is, as we're building single sequence language models to try and get rid of MSAs, the natural language people are trying to add something that looks a lot, is certainly retrieval and looks a lot like MSAs to their neural networks. And so it's just kind of an interesting thing. And I think both are very interesting to explore. But we are starting to kind of see and understand, and we're ultimately trying to activate in a bigger way, these big sequence databases, which really do contain a lot of data, much, much more data than we're going to be able to pull out of PDB, and we're still figuring out how it'll work, but I think it's very interesting. And it's going to also be very, very interesting for some of these problems like variant effects, where it's even more natural than for structure. Now, the other kind of big story, really the much, much bigger story in the last year has been autoregressive language modeling. And this is almost exactly the same as mass language modeling, with what's tiny technical difference, that you're always filling in the very last word of whatever piece of text is given. So you only see context to one side. In examples, Alice was very sleepy, it was time to go to bed might be a good example. Go for a run would be a bad completion there. Or they were out of milk, it was time to go to, and even though it still says it was time to go to, here maybe the store. But you can train this task, and you basically train it to say, what's the next word? And it becomes far, far better than humans at predicting the next word, but that's not really what we wanted. What we really wanted was text. And so the way it goes from here is very, very simple. You ask it for the next word, and then the next word, and the next word, and you build out ultimately a completion of text. And so these, like, if I'm sure many of you have heard or used something like ChatGPT, it's exactly this technology. You're just picking the next word over and over again. And the way people kind of keep score in this field, in the technical sense, is something called complexity, or sorry, perplexity, which is 2 to the number of bits, or you can think of it as the number of reasonable choices for the next word. Technically next token, but I won't go into the word first token difference. And the part that's really, really energized this field is this discovery of what people call scaling hypothesis or scaling laws, which, is really power laws going to machine learning. And in this kind of language model, people think about 3 key inputs: the number of parameters, the amount of compute, like the number of flops used, and the number of words, the number of tokens that are seen, the whole amount of text seen over training. And normally these work on so much data that it never sees the same text twice. And the scaling hypothesis is roughly that you can simply, and I realize I'm running a bit short on time, but you can simply fit a power law to these kind of inputs, and over an enormous, enormous range, you can get a pretty linear numbers are a little more efficient at each side. It's a offset. Uh, it's an offset for the different architectures. So you can think of all your clever ideas as giving yourself a fixed boost. Now, I should say in an really, really need those fixed boosts, but another way to see this is like data plus architecture is kind of your learning system. And if you have incredible amounts of data, you don't have to be that clever with architecture. At least transformers seem to be a very good answer. And really, though, the other thing people found is even though that perplexity line is very straight and smooth, exciting things start happening. Coherence develops, all sorts of capabilities seem to emerge as this very boring, predictable thing happens. Very exciting kind of capabilities emerge. And so people have done this and taken this to very, 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 very large models. So people, say AlphaFold is, quite a few parameters. But says chinchilla, it should be gopher, but a not untypical language modeling size is 280 billion parameters. You cannot even stick the model on a GPU. It's AlphaFold's about 20 million parameters, so it's something like 3,000, 10,000 times larger than AlphaFold. And this is trained on absolutely huge clusters. People figure out what they want to do with the small sizes, and then they do this absolutely enormous run. And these models are incredibly powerful and useful. And so the question is really, does this trick transfer to proteins? Is no one quite knows yet. And there's been some attempts to explore, like Rita and Progen 2 or Progen in general. And this is saying, well, what if we just train this on proteins? Well, they learn everything that we ever wanted to know, including structure, but they won't tell us structure. They'll just have it in there. And can we get really powerful, for example, protein design capabilities just emerging from doing this kind of next token prediction? And I would say here we're still also very early, that we've seen some functional designs, but really in common families, often fine tuning into the family. But really confronting for this, and I think all of these kind of language modeling things say, boy, structural data is hard. Can we just do it with sequence data and then see where we can go from sequence data? And I think it's an exciting area, and I don't know which way it will go. Now, as I get kind of toward the end, and that was kind of what I wanted to say about language modeling, it's all somewhat inconclusive because, I shouldn't tell you about things where I'm absolutely sure of the answer. Maybe diffusion, I'm pretty sure it's a good idea. We just don't know how far it'll go. But then what about all these other problems? And I kind of made a random list of problems this morning that I think will need ML solutions. And I would say most of these, maybe not all of them, but most of them aren't really handled by the main thrusts of AI and ML development. I think that'll suggest that the answers will have to come from within the community that really wants to work on biological problems, or it may not be. Some problems you can maybe pull things down off the shelf, but I think quite a few others will require invention and discovery. And here are questions like, how do we use the sparse experimental data, very, very tiny data sets that make the PDB look huge? How are we going to handle huge complexes, right? Are we going to keep doing ever larger quadratic memory, kind of pairwise networks, et cetera? Are we going to go to sparsity? Cryo-ET is certainly going to be important. It's extraordinarily structural and it's extraordinarily large. How in the world are we going to relate to that as a structural community? Also in kind of interactions, and there's been some really interesting interaction searching and discovery work, but how are we going to handle negatives? How are we going to think about the cytoplasm and all the things that don't interact so that we can really inform molecular biologists and do interaction screening? Can we say anything useful about mutation effects that shift structural populations? You know, a lot of the work on kind of diversity and MSA sampling and, you know, like Bjorn's work is all kind of bringing sampling back. We were trying to build one network that gave one answer, and now sampling is coming back. Is that a feature, or are we just adding really cool things, or is this an opportunity to do something different? And then how do we handle post-translational modifications? And again, kind of uncommon chemistry and related to ligands and all these other things. And the data on all these will be sparse. It will, and like RNA, it will make the protein PDB look huge. And I don't immediately, I can think of some ideas, but I don't immediately see these solutions as coming out of the main thrust of ML development, which is huge models on huge data right now. So yeah, I think that's kind of my idiosyncratic view of some of the places in which we can map existed or kind of the trends in ML research to the problems we have. Yeah, thank you. Can't hear anyone, so.
Okay, we're actually late, but such a good talk.
Oh, sorry.
A few questions, I think. Questions? Anybody got a question? Somebody was there. There's one.
It was comprehensive.
You spoke about the sort of three different components of like model scaling, like, you know, data, compute, and the other one. Do you think that like structural biology, or at least AlphaFold, is kind of like gated by data availability at the moment? For example, if you scale AlphaFold, do you think you would see any meaningful improvement, maybe in the context of like, you know, complexes and stuff like that? Or do you think it's mainly like data gated at the moment?
So there is kind of optimal, there's optimal number of parameters for amount of data. There is more data. I mean, this is something actually we'll talk about later, but you know, retraining AlphaFold is meaningful. There's like 30% more PDB data and 4 times as much cryo data since AlphaFold's training cutoff, or maybe even more than that. I think these are meaningful, but we won't get the kind of web scale training curves. It's not even clear we'll get those on protein sequences due to the limited number of families. Maybe we will with metagenomics, but I think this will lead to some improvements, but I don't think it will be maybe dramatic capability improvements, because we're already using the whole PDB and we're actually seeing the PDB many, many times over training.
Another question? Arne. Well.
These methods needs a lot of compute. So like, I mean, yes. You have it, and Meta have it, and a few other companies have it. So how do you think academia will tackle that? Should we try to like go to Hugging Face, or what should we? How should we even try to use it?
I think it's worth emphasizing these require a lot of compute, even on big industrial AI lab scales. That these kind of big language models are enormous. I don't have the numbers to hand, but they're absolutely enormous. And the answer people have generally taken has been scaling laws like you see on the left, is saying, okay, well, I'm going to make this trend at much smaller sizes, and then I'm going to extrapolate forward. Now you still have to find someone to do the big hero run at the end, or you choose to do it over time. I think that's going to be a part of it. I don't have a really great answer though, because even at like big industrial AI labs, the amount of compute for these models is a limit on how much you can explore and do them, and like you can't do many of these. So it's just no one, no one really knows how to make this a lot better. And I don't know. I don't have an answer there. I wish I did.
England.
John, my question is related to the first question. So AlphaFold has been very successful. It's been widely adopted by the community, and even in this CASP, you can see a lot of many groups use AlphaFold. So the community is thinking about how would you plan to further improve AlphaFold, and when do you plan to release the next version?
I mean, I think a kind of simple like training and data and using more data, I think relatively soon. I think the larger question of architecture and everything else, I mean, one of the things really for us, and one of the things I'm very personally interested in, is a lot of these questions, say at the end or other ones. I think there's a lot on structural biology, but it is worth saying that there are a lot of problems we need to tackle as a community. And I really like, although I couldn't hear the audio, but like redefining kind of CASP as computational structural biology. I think I'm very interested in some of these questions like dynamics, interactions, others, where I really don't even know exactly how to do it, or even maybe exactly what the questions are. So a lot of our effort has actually been towards some of these other questions, and how do we get kind of the AlphaFold type moment on some of these other problems. And we're still improving AlphaFold and have a release soon, but I think we should also like think more broadly that these methods work on problems that molecular biologists care about. What are all the other problems they care about? How are we going to really change the shape of molecular biology? And so that's something I'm very interested in, which I realize is kind of an indirect answer. But I think it is important to think about this and to think about kind of the wide landscape of really important problems that we can apply deep learning and structural understanding to.
Hi, quick question on the EBI AlphaFold / database. You're still missing the viral proteins. Have you thought about adding them, or is that something that you will not do?
Sorry, which proteins?
Virus proteins.
Okay. So there's mainly, I mean, there's two things. There's one where need to do kind of, there's questions about safety and some other things related to this, but there's a more technical point of the polyprotein issue that we don't really know the set of kind of meaningful proteins to predict easily and automatically. Not immediately planning to add it, quite honestly, but it's something that we could do in a future update. Also, viruses tend to have relatively small genomes, so they tend not to be that difficult to predict, honestly. Using the open source tools, you can run through a lot of those relatively quickly.
Thank you.
What about antigen and antibody complex?
It's a very important problem. There's kind of an interesting paradox here, which is that the multimer prediction tools don't look especially coevolution based. That paired sequences are relatively small contributions to AlphaFold multimer, so it seems to be doing a lot of it based on things like shape complementarity or other features, I think, but yet it hasn't done antibody antigen complexes. And I think it may just be a matter of having to drive more accuracy, and it's one of these things that emerges from more accuracy, or it may be some more subtle issue to do with the weirdness of the interfaces, or these are kind of competitive, or they're not co-evolved interfaces. But yeah, that's an important problem. And there's always this question of like, do we come up with really clever new things to solve this? Do we go off and do like energy functions and all this kind of, or do we deep learn harder, find ways to kind of grind our accuracy down, and that's what does it? And I think that's always going to be a question. And the kind of interesting part in the larger AI field has been, well, grind perplexity and everything may happen, or these really incredible, like getting better and better at next word prediction in kind of very predictable ways makes you able to, tell stories about peanut butter sandwiches that are entirely coherent and that kind of thing. So I know I'm kind of stretching to connect that, but I think it is a question of what we will need to do it. And I imagine ultimately it will just be a matter of getting more and more multiple accuracy to make those complexes.
Could I jump in and ask a question? John, all the things you talked about, the language models and things related to that, are for a domain which has a disadvantage compared to our domain. There's no underlying physics, as far as I know, in language or anything equivalent to that. And as you alluded to, clearly AlphaFold is learning some physics in some sense, and that's helping it. Do you see other ways in which the fact that there is underlying physics is going to allow us to do better than you can do with some sort of non-foundational area like language?
So there is an interesting analog to physics in, say, language. We talk about coherence, or, you know, the characters should have the same names over a story, or when you think of worlds, like a world model, in the sense that, you know, in a good story, if you put something into the bookshelf later, the same thing will be in that bookshelf, right? Unless it was disturbed. So there is kind of an underlying world or scene or something else. Also with images, this is a big question with images. Does your image represent a 3D representable world? And so what people have found is that these models are quite imperfect at that, but as they get better at their language modeling task, they get more coherent with the world. And I think that's very analogous to structure in language models. Like, structure is an underlying fact that explains some of the entropy within these protein families, by no means all of it. And as you get better at this, you get the slow emergence of structural knowledge. Now, there's the alternative, which is that we have a small amount of really great structural knowledge, the PDB. And so methods like AlphaFold are pretty directly just exploiting that and ignoring, well, not totally ignoring, we do have the MSA kind of language modeling, but mostly ignoring the language modeling aspect. And in our case, that was enough to, you know, reach this performance level on the problem. So I do think we have an advantage, but I wouldn't say it's totally a unique advantage. It's just that we don't have a lot of, say, scene data or other things that we can train on for language. So maybe I see them as similar, but there is something like physics in the coherence of the world is like the coherence of proteins. But I do think proteins are a more regular, easier problem ultimately than the entire world, which is what language models deal with. And how we can exploit that, I don't know. It's an interesting question.
Thank you. All right, let's have one more.
Thank you for the talk. I just have one question. Yesterday, John Wall gave a talk on the AlphaFold performance in CASP15 and how basically good it was, the sub-angstrom accuracy. I had a question about, did you have, while submitting AlphaFold, if you had like an extra 6 months or a year of innovation time, could you have improved the performance even further? Were there any lingering innovation opportunities that you just didn't have the time to explore before CASP?
Oh, sure. Oh, sure. We were making things 2 weeks before CASP. I'm pretty sure we didn't make the last thing. I mean, it gets harder and harder. Also gets harder and harder to measure really well. I think, you know, you need to go to more and more difficult proteins in order to resolve differences between models. But yeah, I don't think there's anything about AlphaFold that is the final form, and this kind of high complexity set of ideas is the very last set of ideas we'll have. I mean, we see in this CASP, there's more to be done, and I'm sure there's more to be done after this CASP. Now, you know, whether we would do it in 6 months or a year or anything else, I can't tell you, but there's definitely more to be done in this field, although it gets harder and harder to measure, especially on the single sequence problem. The multiple problem is easier to measure because overall we're worse at it as a community, although we've gotten rapidly better.
Okay, on that more to be done note, thank you very much, John.
Thank you.